Hi, everyone. Welcome to Physics 151, lecture number 26. This is the next lecture involving rotational motion, and we're going to start chapter 10 of our textbook and cover about half of the topics in chapter 10 in this lecture. We'll start with the definition of torque, which is the rotational equivalent of force. Then we'll move into applications of that involving Newton's second law. We'll revisit the work energy theorem for rotating systems. And then we'll look at the special case of zero net torque, which is the case of equilibrium. I'll be showing about 3 worked examples from the sample problems in tutorial number 26. So first of all, we might ask ourselves, what is the quantity that plays the equivalent of force, but for a rotating object? And well, the answer is there is basically a twisting equivalent for force, right? And it is called torque, is the name that we give to it. It is any sort of twist that attempts to rotate an object about an axis of rotation or an intended axis of rotation in case the object hasn't actually started to move yet. Almost every problem like this is going to have some natural pivot point or fulcrum or something that would serve as an axis if the object already were spinning. How do we generate torque? Well, most of the time, torque is generated when there is a linear force, F, just like the kind we're used to already from our previous chapters. And it acts on an object, an object either is rotating or could be rotating. And if it acts on that object at some distance r away from the intended pivot or the intended axis of rotation. So you can see here, I've drawn a couple of sample r vectors here. So for force A, it's acting at a location that is this distance away from the axis. For forces B and C, they're acting at a different location. So they're at a different distance r. R is the vector that goes from the pivot point to the location where the force acts. The amount of twist or twisting force, torque, that is generated by any one of these forces is equal to the strength of the force in newtons times the distance of that force acts or is applied from the pivot, times this factor of sine phi, which is basically a measure of how perpendicular the force is to the vector r. I'll say more about that in just a moment. Note that the units of this quantity of torque in MKS units are going to be newtons times meters. And then the sign here is dimensionless. We don't have a special name for this, so we just call it Newton meters, or sometimes meter newtons. But we never, even though this is mathematically equivalent, it looks mathematically equivalent to energy, we would never, ever, ever write joules as the unit for torque, and it would be incorrect to do so. The British units or imperial units for torque are, again, a force times a distance or vice versa. So you hear pound feet or foot pounds as the torque, as the unit of torque for imperial units. When we break down this equation a little bit, we can see that we get more twisting force or more torque when, of course, the force is stronger, right? That increases our value of F, or the value of R is increased. Another way of saying this is the lever arm is larger, although I'm not using the quantity of lever arm itself in this definition here. Please see our textbook chapter if you'd like to see more about that. So in other words, if we apply the force farther and farther and farther from the intended axis of rotation, we get more and more torque. That's why we put doorknobs as far as possible from the hinge of a door. That way you get the maximum possible torque when you apply a force to the doorknob. And then finally, this phi term here is defined, this angle phi is defined as the angle between the direction of the vector F and the direction of the vector R. So we can see here for force A points to the upper right, RA points to the lower right, and the angle between their two directions is 90 degrees. Sine of 90 degrees is 1, and that's the largest possible value that this sign can have. So what we see is that the greatest torque is obtained when the force that's applied is at 90 degrees or perpendicular to the vector R. So again, if we think about pushing on a door, if you push as perpendicular as possible to the door itself, then because the vector r runs along the door, from the hinges along the door to the handle, then you will get the greatest possible torque. However, if the angle between F and R is either less than 90 or greater than 90, so if the person were to pull at an angle like this, then that would be an angle phi that's less than 90. Or if a person were to pull or push at a direction like that, then it would be an angle phi that's greater than 90. And in either of those cases, the sine of the angle drops below 1. It becomes 0.8 or 0.7 or 0.5. And we end up having a torque that is less than the maximum that it could possibly be if the force were perpendicular to R. Finally, if you apply a force that is at 0 degrees, meaning if we pulled on the wrench, suppose the wrench actually looped all the way around the bolt, right? If we were to pull on the wrench away from the bolt, that would be at phi equals 0 degrees. Or if you look at force C right here, force C, if you push directly toward the bolt, force C is at 180 degrees. In either of those cases, sine of 0 or 180 is exactly 0. So in that case, you get no twist whatsoever. So once again, if you push directly inward on the end of a wrench, you get no twist on the bolt, one either clockwise or counterclockwise. We get no torque. This the way to use this formula will make a little more sense when I show how to work problem number 1 on our sample problems. Now, how do we use torque? Well, think about any equation that we have from translational or linear motion where the force F appears in the equation. In this case, I've written here Newton's second law, which is the main expression that we're going to use for dynamics problems. In that case, we can follow the same sort of pattern we did before, where we think about what's the rotational analog for each of the quantities, each of the variables that appears here in the translational equation. So I think about acceleration. We can replace that both angular acceleration, mass gets replaced by moment of inertia, and then of course the net force gets replaced by the net or sum of all the torques acting on the object. So what does that sort of mean in practice? Well, here's a little cartoon of two children on a seesaw. And this is a seesaw that's assuming that the plank of the seesaw itself has no net, has no mass. So let's assume that the mass of the seesaw is tiny compared to the mass of the two people. In that case, each of these people has a weight, and each of those weights creates a torque about the pivot or fulcrum, the intended pivot or fulcrum, at least here, if they're not moving yet. And we need to add up this counterclockwise torque here caused by person A and the clockwise torque caused by person B. And if we sum all that up, that will tell us how quickly the entire system is going to accelerate in an angular fashion about the pivot, about the intended pivot. By the way, if we're going to add torques that are in different directions from each other, some counterclockwise and some clockwise, you may remember from one of the previous lectures that our sign convention for rotational quantities is that counterclockwise quantities are positive and clockwise rotational quantities are negative. So this is, again, following the standard or the convention from trigonometry. As you think about theta, think about the unit circle, positive theta increases in the counterclockwise direction. So we're following that same convention here. So what that would mean is in the case of this teeter-totter problem right here, we would make torque A a positive torque, and we would make torque B a negative torque. And that's how we would sum them up. And this plus or minus sign convention here becomes a bookkeeping device for us to make sure that we're not going to accidentally sum these two torques in an additive way. We want to make sure that these two torques will counteract each other because they are in fact twisting in different orientations, in different senses. If I look at this other sort of beam right here, this beam is mounted on a pivot right here. And you can imagine that there's one force acting downward, right? Force number one, and force number two acting off in this upper leftward direction like this. And force one is attempting, if point O here is the pivot, maybe a hinge on which about which this beam is mounted, then we can see that force number one is going to attempt to swivel this beam in the clockwise direction, whereas force two is going to attempt to swivel it in the counterclockwise direction. So that means force one is exerting a clockwise torque on the beam. Force two is exerting a counterclockwise torque on the beam. And we would, again, we'd want to add them this way. Negative for the clockwise, positive for the counterclockwise. Rotational for work is defined for a torque acting on a rotating object, very similar to the way that work is defined for a force acting on a translating object. So you may remember, if we think back a few lectures, that work is defined as a force, the strength of a force, times the displacement of an object, times cosine of the angle between the direction the force acts and the direction that the object displaces. So notice that the way phi is defined here is very similar to the way it was defined a few slides ago here for torque. The only difference is that for torque, we use a sine function there instead of, in this case, for work, before, we had a cosine function. If we think about the rotational analogs again, force and displacement get replaced over here by torque and angular displacement. So those two quantities are pretty much just substituted by their rotational analogs. And then remember, if in the case of a translating object, if the force acting on it and the displacement it undergoes were in exactly the same direction, then phi was 0 degrees and cosine of phi was 1. On the other hand, if the force and the displacement were exactly opposite directions, remember for friction, on a sliding friction on a surface, that was always the case. In that case, when the force and the displacement were exactly opposite to each other, phi was 180 degrees and the cosine of phi was -1. Those are the only two possible cases for a torque and an angular displacement. Okay, so if you think of like a merry-go-round or a wheel that's rotating, it's possible for a torque to act either in the same direction that the spinning object is displacing or in the opposite direction that the spinning object is displacing. So those are the only two possible cases here. It's not possible for us to have a torque that is in some other direction other than either aligned with the angular displacement or opposite the angular displacement. So in the case, if we have a merry-go-round example again, if we have a kid who is pulling on the merry-go-round in the same direction that it's spinning, then that child's going to do positive work on the merry-go-round because we'll choose the plus sign here when torque is in the same direction as displacement. On the other hand, suppose there's friction acting on the bearing of the merry-go-round, or suppose that there's air drag or something, acting on the merry-go-round. In that case, the torque caused by that will be in the opposite direction of the angular displacement of the spinning object of the merry-go-round. In that case, we choose the minus sign. What do we do with the work done by a torque or caused by a torque? We'll do the same thing with it like we did with the work done by forces acting on a translating object. If we add up all of the works done by all of the forces, we can sum them together, find the net work done on the object, and that will tell us the change in kinetic energy of the object. That was the work energy theorem. It's just that simple, straightforward statement right there. The same will be true for a rotating object. If there's one or more torques acting on a rotating object, we can add up the net work that all those torques are doing, and it will result in the object either spinning faster or slowing down, right? So it'll spin up or spin down, depending on whether there's net positive or net negative work. Finally, before we do examples, let's talk a little bit about the special case of Newton's second law when the net force or the net torque is equal to 0. So you might recall before that we called that particular special case equilibrium. And we sometimes just call it dynamic equilibrium when the net force is equal to zero. We call it static equilibrium specifically in the case where a system sits continuously at rest. So if the object or objects or system, the whole system of objects that we're interested in, if nothing is moving and it continues to stay at rest over time, then we call that specifically static equilibrium. Otherwise, just generically, the term equilibrium just means a situation where the net force is equal to zero, but the object could perhaps be in motion at a constant velocity. That would also be true, or could also be true when the net force is zero. But it turns out that just making sure that the net forces on an object sum to zero is good enough for some types of problems. So there are some statics problems where that's all you need in order to solve the problem fully. However, that is not the case when you have something like a seesaw or a teeter-totter. So in that particular case, we might say, okay, if, again, this is assuming that the seesaw or plank itself has negligible mass. So let's assume it has no weight. The only forces acting on the seesaw then are going to be the weights of the two people, person A and person B, and the upward force of support from the fulcrum. So there's this contact force here from the fulcrum. So those are the only three forces acting on the plank of the seesaw itself. Now, if the seesaw is balanced, if it were balanced, then what must be true? The sum of all those three force vectors must sum to zero. All right, well, great. That tells us something about the system. It tells us that the upward force from this fulcrum must be equal to the sum of the weights of the two people. But it doesn't fully describe the system. For example, if I were to tell you where person A is sitting, how far person A is sitting from the fulcrum, can you solve for me how far person B should sit? Well, no, just by summing these vertical forces acting on the seesaw, I don't have any information about where these forces are positioned in the x direction, or along the plank. In order to solve for that and to fully describe this equilibrium, we need to also invoke this, that the sum of the torques must also be zero. And when we talk about summing the torques, we mean summing the torques about any choice of pivot or rotational axis that we might choose for, along this system. So there's, in the case of a seesaw, there's sort of a natural choice of a pivot right here at the fulcrum. But sometimes for some equilibrium problems, static equilibrium problems, it's not obvious where to choose the pivot. And in fact, we might try writing this expression for the net torques equal to zero multiple times, choosing different locations along the system or the object as the pivot. And finally, and some of those locations will end up giving us more information or make our math easier. And other locations might make our math harder or give us sort of less information or some trivial statement like zero equals zero. So in this case, we have an obvious sort of choice of pivot. So here, it's really easy to pick. In that case, we need to say, all right, it's not just enough to sum the forces and say that's equal to zero. We need to sum the torques and say that the sum of plus torque A minus torque B must be equal to zero as well. And in that case, when we solve for each of these torques, we have to use the distance r that each of these people is sitting from the fulcrum to get those two torques. And that will allow us to then, given one of the distances, solve for the other distance, for example. As a side note, the sum of these torques about any pivot, suppose we choose the pivot to be here at the fulcrum, right? The sum of these torques will equal zero only if the fulcrum is positioned directly below the center of mass of the two people. So if the two people are the system of masses here, then only in the case where this fulcrum is positioned right below them will torque A minus torque B happen to sum to zero. If we were to move the fulcrum over one direction or the other, then what we would find is there would be an excess torque in one direction or the other, and the net torque would not sum to zero. So it turns out that we can predict whether a system will be balanced either by summing all the torques, or if the system if all the torques in the system are caused by the weight of the objects in the system and not by other forces like people pushing or springs applied or other things like that. If it's just weights of things like the weights of these two adults, or if you imagine like a mobile where you have objects hanging under their own weight, then that system will be balanced as long as there is a support from below or a suspension from above, like a string or something, that's right at the center of mass of the system of the weights. And then it will be balanced. So it's kind of a shortcut. You can use our center of mass equations from a few lectures ago to figure out where the center of mass of the system is, and that will tell you if it's balanced. The next few slides don't have any equations on them. This is just introducing some concepts and a little more vocabulary that you're very likely to encounter again, both in Physics 151 or 152. And that is the idea of stable versus unstable versus neutral equilibrium. So if we think about equilibrium, right? Equilibrium is any situation, like we just said on the previous slide, where the net forces sum to zero and the net torques sum to zero. That's the definition of equilibrium. So we could think of a lot of situations where that is true. We could think of a mass at the end of a relaxed spring. In that case, the sum of the forces acting on this mass is zero. We can think of a pendulum hanging straight down. And at the moment that it's hanging straight down, the tension upward and the weight downward exactly sum to zero. So these are equilibrium situations: a mass at the end of a relaxed spring, a pendulum hanging straight down, a marble in the bottom of a bowl. At the moment that it's at the bottom of the bowl, again, the normal force and the weight exactly sum to zero. Or a boat or anything that's floating on the surface in equilibrium on the surface of water. In that case, the upward force of buoyancy and the downward force of the weight of the boat are exactly summing to zero. So these are all cases of equilibrium. Now, what makes these four examples stable equilibria is that if we nudge the system a little bit in one way or the other, in one direction or the other, in any direction really, right? This is sometimes called a perturbation, if we perturb the system a little bit from its equilibrium point. So if we give it a small displacement, then the system will respond with a restoring force or a restoring torque that attempts to restore the system back to its equilibrium position. So the net push on the system will, after we displace it and release it, the net push will be back to the equilibrium position. So we know that if we take this mass at the end of a spring and either push it to the left or pull it to the right, in both cases, the force that arises on the mass or on the system is back to the equilibrium position. The same thing is true for a pendulum. If we take this ball that's hanging straight down and perturb it in any direction, then the net force that will arise on it, that will be to try to push it back to its equilibrium position. This can also be thought of as a net torque, because we have a force at the end of this sort of lever arm right here. So the net torque will be to pull it back to the equilibrium position. Same thing is true for the marble on the bottom of the bowl. Same is true for the boat. If we were to take the boat, push hard down on the boat and just push it further into the water and then let go, what will happen is the buoyant force will grow, but the weight won't change, and it will try and push the boat back up after we release it. If we were to lift the boat up a little bit, then the buoyant force will shrink, the weight doesn't change, and the same thing will happen when we release it. It'll go back to the equilibrium position. These are all stable equilibria because small displacements result in restoring forces or restoring torques. Unstable equilibria are, again, they start with an equilibrium, but if you displace or perturb the system a little bit from that equilibrium position, the net force or net torque that arises will be in a direction that is away from that original equilibrium position. So what that means is the system will depart from that equilibrium and never return. So what we have here is, again, a small ball or marble on the top of a hill. At the very top, the weight and the normal force are exactly balanced to zero. But even a slight perturbation in any direction will cause a net force away from the equilibrium position, and it won't cause a restoring force. It'll cause sort of a departing force, if you will. A pencil balanced on its point is once again in equilibrium, but even a small displacement in any direction will cause a net torque that is further away from the equilibrium position. See here how the pencil's weight now is causing a net torque about the pivot point that is trying to depart the pencil even farther from its equilibrium position. So these are all unstable equilibria. There is a sort of a third class of equilibria that's given the sort of generic name neutral equilibrium, because if you imagine like a ball resting on a flat horizontal surface or a book resting on a flat horizontal table, then if you displace the book in any direction a little bit, it will find a new equilibrium at that new position. And it has no preference for staying in that new position versus returning back to the old position. It's perfectly happy at the new position. So here's a sort of an overall illustration, right? This cone standing on its base is in a stable equilibrium. If you tip it a little bit and release it, it will return to the equilibrium position. A cone balanced on its tip is in an unstable equilibrium, technically in equilibrium at this moment, but the slightest perturbation in any direction will cause a permanent departure. A cone lying on its side, so if you're looking at the base like this, or you could think of this as a sphere or a ball or anything like that, if you perturb it a little bit in any direction, it will simply find a new equilibrium at that new position, and it won't have a net restoring force or a net departure force. It just stays at the new position. So that's a sort of a neutral equilibrium. Now, if we think about an object that is in equilibrium, and then we try and tip it over, okay? As we were just talking about sort of with this cone here. Okay? If we introduce a concept which is called the base of support, if you were to draw an outline between the farthest reaches of the parts of an object, or the points of an object that are touching the floor, then the region bounded by those legs is called the base of support of the object. So the base of support of a person is bounded by the outer limits of that person's feet, and all the region in between is considered the base of support. For a chair or a table, it's a region bounded by the legs. For a car, it's a region bounded by the four tires. Okay, so the base of support would be underneath these tires right here, or underneath those tires right there. Now imagine that we were to take that object. Oh, and here the base of support is the region under the corners of the fridge. So this is the base of support as it tips, right? Imagine if we were to take that object now and start to tip it over, okay? If we tip it a little bit, well, and release it, we know it's going to simply right itself, right? But if we know that if we tip it a lot, we know that it will topple over and it will not return to the equilibrium position like it would if we tipped it a little bit, but instead it departs from the equilibrium position. So there seems to be a sort of a boundary point here in between a small perturbation and a large perturbation, right? And so what's happening there is, well, one way we can model this is we imagine where the center of mass, or center, also known as center of gravity of an object, is. And when an object is in a uniform gravitational field, those are the same thing, center of mass and center of gravity. If we think about where that is for an object, and imagine that it is, or look at where that is when the object is tipped by just a little bit. As long as that center of gravity still remains over the object's base of support, then that is the criteria necessary. So that if you release the object from rest in that position, the net torque will still be back to the original equilibrium position, and the object will right itself. So the example of this red sports car here, even though the sports car has been tipped up and tipped over, notice how the center of mass, or center of gravity, is still over the base of support of the car. So as a result, if you were to release it from rest at this position here, it will return, it'll right itself and return back to its original position. However, if you tip the object further, then far enough that the center of gravity passes just beyond the base of support. So notice here, the base of support is off to the left, but the center of gravity or center of mass is now beyond that base of support. So it's now outside of the base of support. In that case, the net torque now about the pivot, which is this corner right here, is going to be away from the original equilibrium position, and it will depart and it'll go off into some other state, right? Some other position, not return back to the original equilibrium position. And that's true of this little green car right here. Notice that the center of mass, center of gravity, this little green car is just outside the base of support of its tires. So when this little car is released from this position, it's going to tip away from the original equilibrium position. It is advantageous if you think that an object might occasionally tip. It's advantageous to try and place the center of mass or center of gravity as low as possible. And what that means is the object has to tilt to a greater angle before the center of gravity crosses this unstable equilibrium point right here and crosses over beyond the base of support. So that's why, you know, a person down in a crouch has a lower center of gravity position than a person that's standing all the way up. And it makes it harder for this person to be tipped over, right? The person who's standing all the way up, all you have to do is tip this person by a few degrees and their center of gravity will go outside their base of support. And then when released, they'll fall over. But here, the person would have to tip by more degrees to get that same thing to happen. And the same thing is true of the sports car with the very low center of gravity. So that way, this sports car would have to be tipped up to maybe 60, 70, 80 degrees before the center of gravity passes beyond this tire here. Whereas this could be like a Jeep or an SUV or something where it's a relatively tall vehicle and the center of gravity, and maybe the wheels are even close together. And so the center of gravity can very easily pass outside of the base of support, even when it's only tipped by less than 45 degrees, for example. And then it makes rolling more likely. So widening your base of support and lowering your center of gravity together means you can tip to a larger angle before your center of gravity passes outside of your base of support. So that's when you cross over from the stable to the unstable regime. All right, so for the rest of this recording, I'm going to show 3 worked examples, problems 1, 3, and 4, that will illustrate several of the equations that we just went over. So I'm going to pause the lecture now, and just to keep the video files a little shorter, and I'll start a fresh video file with these 3 problems.